It's really good coffee, so we go almost in contact. But maybe the food is really good. People is slowly coming back. Some of them they're just finishing the smoking. What about habit? Okay, so we are going to start the very last session of the meeting. The first talk is by Silvia Dossi, who's been talking about wind evolution on this phase of the from AGB2 planetary nebula. I found the title extremely interesting, and I hope you do so.
Okay, so I want to start thanking the organizer for giving me the opportunity of giving this talk, which is about the wind evolution of low and intermediate mass stars, which follow an evolutionary history similar to this one, which is an evolutionary track calculated through the Hadron stellar evolution curve. And everybody knows very well how important is the asymptotic giant branch phase. In fact, it is here that most of the envelope is released into the interstellar medium. And the material ejected really reflects all the nucleosynthesis and mixing processes that were active during the AGB evolution. And for this reason, this also affected the chemical evolution, the feedback process within the galaxy, and also the infrared emission of the galaxy. So they really have an important role among the universe. And despite their importance, there are plenty of open questions, such, for example, the mass loss and the production mechanism. And the AGB and the planetary nebula phases has a unique opportunity, offer a unique opportunity to infer new information about the previous AGB evolution. In fact, most of the dust that was produced during the AGB phase is still observable during those later phases, and the chemical composition not significantly alter after the AGB phase. So we can use them as a probe of the previous AGB evolution. So it is important to understand which kind of material can be ejected from the previous AGB phase. And this material really depends by the hot bottom burning and the jump episode. And I'm specifically interested that you understand how vary the carbon surface composition. In fact, the hot bottom burning decrease the carbon abundance while the third jump increase it. And why I'm so interested in understanding that? This is because of the presence of the CO molecule, which is extremely stable and entirely locked element less abundant between carbon and oxygen. And then this is the reason of why in the environment that experiences several third jump episodes but do not experience the hot bottom burning process, we have a lot of carbon available to condense and form dust, and for this reason we have more dusty species such as solid carbon and silicon carbide. So we are able to understand which kind of material can be ejected from the AGB phase, but how can we follow the evolutionary sequence of the wind? A very beautiful way can be through the spectral energy distribution study. Indeed, here I will show you, for example, of an AGB, post-AGB, and planetary nebula using the same color coding. So the black line are the synthetic spectrum that I am obtaining for the AGB and the post-AGB using the dusty transfer code, while for the planetary nebula I used cloudy. The colored line are the observed spectra, while the blue squares are the observed photometry. Basically, we understood that the AGB phase is the one in which is active the dust production. In fact, we have this huge mass loss by the star, low effective temperature, so a perfect environment for the condensation of dust. For this reason, the dust will be also very close to the central star, and we are not able to disentangle the dust emission from the central star, and this reflects into one huge peak in the SED. Then, thanks to the radiation process, the radiation of the star, the wind will achieve farther and farther distances with respect to the central star. The dust will achieve lower dust temperature, and for this reason will have this peak at infrared wavelengths. At the same time, the star will start the contraction process towards the white dwarf stage, so also the peak of the star will shift to shorter wavelengths. This configuration, which is named shell-like type CD, is even further highlighted through the planetary nebula phase, in which the dust has achieved even further distances. The star will achieve also higher effective temperature, and now we have also the emission of the nebula. What I want to, the key message that I want to give to you is that by studying different regions of the spectral energy distribution, we can derive different type of information. From the optical or the UV region here, we can derive information about the star. From the infrared region about the dust, such as, for example, the dust mineralogy, the amount of dust that is present nearby the central star, or the dust temperature. While for the planetary nebula, we are also able to understand how much gas is present inside the nebula itself. So even if we are able to understand the properties of the star and the dust and the nebula, how can be sure that different objects can follow with the same evolution? So how can we compare different type of objects? We can do this through combining both the HR diagrams and the chemical abundance studies. In fact, these are three sources. In magenta, the planetary nebula 1, in the green post-AGB source, and this orange here is an AGB star. These are evolutionary track of Aton, both here and here in black, for different progenitor mass. And what we have is that by combining the luminosity and effective temperature that I derived from the SED modeling, we can achieve a mass loss progenitor that is in agreement also with the observed chemical abundance. This is an example for carbon, but we also looked at nitrogen and oxygen. So what we can find, therefore, is that we can find different objects that likely followed a same evolutionary history, or at least very similar. So we are able to compare, for example, the dust that we observe here in the Planetary Nebula phase with the AGB, and the dust that we observe during the post-AGB with the previous AGB phase. So let's start making this first link, and I want to remember you that we are looking to carbon-rich dust, and specifically I am interested in those that follow with a single stellar evolution. So this is a diagram in which I'm comparing the luminosity, which for the post-AGB directly correlate with the progenitor mass. In fact, if you see this here, this is the post-AGB phase, and this is an evolutionary track of 1 solar mass, 1.2, and 5 solar masses. So the larger is the luminosity, the larger is progenitor mass. So luminosity, which correlates to the progenitor mass, correlates also with the amount of dust that we derive from the SED modeling during the post-AGB phase. This is something that is in total agreement with the previous AGB models. In fact, the larger is the progenitor mass, the larger will be the number of third-degree predictions that are experienced by the star, surface carbon, and mass loss rate, and therefore the amount of dust that we produced. From this diagram, we can also understand something else. In fact, if we look to the color coding, those sources, which are the metal poor ones, are characterized for a fixed luminosity, so for a fixed progenitor mass, by higher value of the amount of dust nearby the central star. This is due to the CO molecule. In fact, larger metallicity means that we have larger amount of oxygen available, so the lower will be the excess of carbon available to condense into this higher oxygen abundance, so this CO molecule. We compared the amount of dust that we observed during this post-AGB phase with the previous AGB modeling, scaling, of course, the amount of dust that we could derive, assuming the mass loss prescription for a carbon-rich star, which is the one from water. And what we found is that from this comparison, so amount of dust derived from the SED modeling and the scaled amount of dust that we can derive from the AGB modeling, we can find an agreement for the massive carbon-rich star and for the low mass and the more metal-rich sources, but for the metal-poor sources, this consistency was not found. In fact, it was necessary to enhance the mass loss rate at deep AGB phase, so it means this quantity here, by a factor of 3/4. So what we suggest is that we have to enhance the mass loss rate at the deep AGB phase for the low mass and low metallicity sources in order to achieve a mass loss rate at the deep AGB phase by a factor of 3, 4, 10 to the minus 5 solar masses per year. So we could ask ourselves, nice, you find this solution for the post-AGB phase, but what about the planetary nebula sources? We can find a solution from this diagram. In fact, this is the progenitor mass, but be careful because this is the progenitor mass at the beginning of the AGB phase. This is not the initial mass. And this is the amount of dust that for the full symbol is the amount of dust that I derive from the SED modeling, while the open symbol are the amount of dust that I derive using the Aton modeling. From this diagram, we understand again that the larger is the mass, the progenitor mass, and the larger is the amount of dust. But we also understand that, generally speaking, the amount of dust that I derive from the SED modeling is lower than the SED modeling is lower with respect to the one that we can expect from the previous AGB phase. So probably there was active some dust destruction event. So we don't know if it was photoionization, but some we have. For sure there is less dust with respect to what we could expect. The only exception for this behavior are those sources, which are the low mass and low metallicity sources, so exactly the same, for which we found the necessity of enhancing mass loss rate for the post-AGB sources. So probably we have two evidence of the necessity of enhancing the mass loss rate at deep AGB phase for this kind of sources. The evolution of the wind from the AGB to the planetary nebula phase can be, of course, studied also through other diagrams. For example, from the color corridor diagram, and this is an example with the Spitzer. In gray, the gray triangle are the GB sources, the blue squares are the post-GB sources, and those are the planetary nebula ones. Those full lines are the synthetic evolutionary track that we again obtained using the Atom Stellar Evolution Code. And what we can understand from this diagram is that this is the free solar mass track, and this is the true solar mass track, that only the more massive sources can achieve redder colors, and this is again consistent with the previous AGB evolution, because again we have the sources that are more massive, that have experienced more Teradja episode, more dust, redder colors. This is something that was already studied in the literature, but what we suggested recently is that the sequence of the AGB phase can probably continue with this dashed track. In fact, these two sources were already studied in the literature as sources that are AGB, that likely are ending the AGB evolution, and they are entering to the post-AGB sequence. And in fact, by adding the information of the dust temperature that we derive from our SED modeling, we find that there is a nice sequence starting from the sources that are very hot, so in which the dust is just formed nearby the central star, so the AGB stars, and then cooling the dust until reaching temperature around 100 of Kelvin during the planetary nebula phase. So to conclude, what we can say is that the post-AGB and the planetary nebula phases are really wonderful sources to find new information about the previous AGB evolution. They keep some signature about the dust formation. We suggested also the fact that is probably need this enhancement of the low mass and low metallicity sources at the tip AGB phase by a factor 3-4, so to achieve a value equal to 3-4 × 10⁻⁵ solar masses per year. And I want to say that in our group we are already calculating the new evolutionary track with the Atom in order to understand what is happening. So stay tuned for that, because we already have some new results. So a paper is coming. And as a future perspective, I already asked to achieve some new spectra with the Large Binaural Telescope, so I will be able to expand the post-AGB sources. And of course, I'm also looking for a nice James Webb CCD to understand even better this transition from AGB to the planetary nebula phase. So thank you for your attention.
Grazie mille.
Yes.
Perfect timing. Now it's the time for questions. Okay, Marcelo.
Thank you very much for the presentation and for the work of this ILOI. The question, when you say that you propose an increased mass loss rate, is it an increased mass loss rate in relation to what? Is it related to the one you assume in the modeling, like the Bachtel thing, or is it something else?
Yes, basically, so what we have is that during to model, of course, the evolutionary track, you assume that the mass loss prescription, which is the one of Wachter, no? Okay. Which follow this formula more or less. So steeply dependent by the effective temperature as a power of -7, and there is this quantity here. Which is the mass loss at the tip AGB phase. So what we suggest is to basically change this factor here in the mass loss prescription in order to achieve a better consistency, but it's only for this kind of sources is needed.
Then the question will be, because the Bachtel models were really a limited theoretical grid, if I remember correctly.
The Wachter, yeah.
Have you tried using like a semi-empirical mass loss rate, like the ones derived by Groenewegen in the late 90s or something like this?
Yeah.
So in my experience, they did a quite good job of that.
Yeah. So the reason of why we are using the water mass loss prescription is because it really takes care about the CO abundance. And since we are looking to the sources that are really full of dust, so our pack, the CO sulfur composition really affects the wind that we can achieve. So this is the reason of why water. We have tried the other mass loss prescription. For example, we saw that for the oxygen-rich sources, the Bacillus and wood is perfect. Also the blocker relationship for the oxygen-rich sources again, but for what concern the carbon-rich experience in our sources, in our experience, the water is the best, but yeah, we can still try also other. But at the moment, we explore those three mass loss prescription.
Thank you very much.
So estimating mass loss rates from dust is always has this issue of what is the gas to dust mass loss rate, gas to dust ratio, right?
Yeah.
So first question is, what have you assumed for the gas to dust ratio, and is it possible that some of the differences between your different classes of massive or less massive stars could be due to changes or difference in the gas to dust ratio rather than the mass loss rate itself?
Okay, so but you mean in the evolutionary track? Okay, no, because what we are doing is that in order to monitor how evolve the dust, we assume the dust formation with from the Heidelberg group. So this is a combination of both the this dust vaporization and dust formation, given the temperature of the star and the abundance, the mass loss. So from what I know, we do not have to assume the dust to gas ratio. Still, we can check. We can talk about that later, probably. Yeah.
Dusty has a default
Okay.
already built in it, but it provides scaling relationships so that if you think that your gas to dust ratio is different, then you scale your result based on that. So there's a default in it.
The
So you
class
just use
model
the-
smoke, the gas and the dust, so you don't need to assume any dust.
In fact, I don't think that.
Sorry.
You don't need to assume any dust, the gas and dust of dust, the gas ratio, because she's modeling both the nebula and the.
No, you're-
Yeah, for example, maybe this is the don't DGBs. Yes, for what I can say is that from what concern the post-GB sources, we do not have to assume this dust to gas ratio, and we derive the dust to gas ratio for the planetary nebula phase. We also derive the dust to gas. I think that this is an output from the code. I'm quite sure about that. We do not have to assume that, but it is an output by combining both the atom cell evolution code and the dust modeling information. But we can have a chat later and check in better for this information.
Okay, so we keep the discussion later for these
Yeah.
questions. Thank you very much.
Yeah.
Silvia. Then next speaker is Senkul Jalgi, talking about dust and gas in planetary literature. So maybe she's going to ask more about questions.
Hi, I'm Şengül Yalgın from Ankara University, and I'm a PhD student. I will be talking about tracing planetary nebulae evolution through dust gas diagnostics and I used four parameters. We used four core parameters: plasma diagnostics, excitation, dust to gas ratio, and elemental abundances. All the data here, as you can see, were previously examined in our project. And the data plus electron temperature, dust temperature, and dust to gas ratio, also the total ionic mass related to our sun is estimated in this work. The data previously obtained data were obtained using Russian-Turkish telescope RTT 150, that is 1.5 meter telescope at Antalya, Turkey, using the instrument to detect faint object spectroscopograph and camera. And here in this study we observed 16 compact planetary nebulae. And all the emission lines, the prominent emission lines here, as you can see, the most prominent ones are hydrogen alpha and doubly ionized oxygen, and all these lines were modeled in detail through photoionization simulation using cloudy code. In order to do that, we use the emission lines as observational constraints also together with them here. The IRAS and TWICE bands, also the radio frequencies, and angular diameters were introduced to the model as observational constraints, inputs, then effective temperature, luminosity, and dust to gas ratio and grain abundances treated as variable parameters, and we obtained these sets spectral energy distributions of our models. Before we carried out this study, all the objects were initially defined in hash database as possible planetary nebulae, likely PNE or new candidate. Then what we have done in order to classify them as true PNE, we use the emission line ratios, and to do that we use Savadin, Minello, Bianchi, and Baldwin, Phillips, Terlevich diagrams. These diagrams use the emission line ratios of doubly ionized oxygen, ionized nitrogen, ionized sulfur, and also hydrogen alpha and beta. Then, as you can see, as the red points, all our sample are approved as true PNE objects. Here, what does these bombs making peak at nearly 330 micrometer is these bombs are related to the gas emission, so they are mostly aliphatic carbons, polycyclic aromatic hydrocarbons, they may be, and also fullerenes, and also rock, okay. Everything has environment. Also, they can be attributed to silicium carbide, but they are mostly magnesium sulfate. All the others may contribute to this bump. Okay. what is new in this work is beside the other parameters I had already told you, we obtained the excitation class of all the objects using the scheme of Reid and Parker 2010. And we also estimated the plasma temperatures and densities in the low and in the high range. Also, dust temperature in the low and high range. Also, we obtained total ion mass in our nebular sample in the ionization region, and also dust to gas ratio by mass. So here, in our future work, we intend to study with a few hundred planetary nebula. What I will be showing here is just a kind of play, a try. To check the trends using only 60 nebula. What we would expect to see when we use hundreds of objects. So, which means that whatever trends you see here does not mean that they would be theoretically in this way, because we here depend on only 16 objects and some of them are already outliers. You would ask me later why they are outliers. So let me start it off here. At the top left panel, we see the correlation with high dust temperature and highest dust temperature and highest electron temperature correlation. Why we check this correlation to understand whether there is homogeneity in our sample. So let's say if we didn't find the homogeneity, as you can see here, two objects 50 and two objects do not show this. So if there are outliers, such kind of outliers, it means that the dust is generally not homogeneously distributed, but stuck in the geometry in different optical depths. We also check this for the low range of dust temperature and electron temperature, and here we see similar, somehow homogeneous, we can say, but for highest ones, the trend is better. And here on the top right panel, we compared dust temperature with high electron temperature, but this time by using the mass spins. Here we see that low mass objects and high mass objects trends show difference. The having low mass objects, the trend we see here as the dust temperature increase. They are negatively correlated, but when we go to higher mass, they are positively correlated. Here, when we, when we make a relation with dust temperature and age, for the low dust temperature, we see no trend for age, but for the high dust temperature, somehow still we do not. I will be faster. And when we correlate dust temperature with electron density, here, as we expected, theoretically, the more dense the object, so the dust temperature increase, they are positively correlated. And we here on the right top panel, what we see, the effective temperature and the excitation class of the sample. So, as we know, we expect for low excitation, low temperature for low excitation. As the temperature increase, excitation increase, but here, what is strange for me, I will later examine the answers, or maybe we will talk here. When I use the theme of rate Parker 2010, the using the theme A class and excitation numbers, the trends show difference. I think maybe it's because our data is mostly scattered. That's why scattered. That's why this difference may occur. Also, I have already told you there are outliers in our sample, a few outliers, and so I already explained this. The H here, as we expect, for as the nebulae gets older, is central star get more the temperature increase, so we expect higher excitation. And on the other hand, for higher mass objects, in our sample, higher mass objects are older ones, and the young ones are low mass objects. So that's why we obtain this trend. The bottom, top, and which is also what is expected for a dust to gas ratio. So my time is about to finish, yeah. And here we see the relation. Okay, I have already talked about this, but I didn't talk about this is this elemental trends. So we compared the dust to gas ratio with nitrogen, oxygen, sulfur, and also helium. So what we have seen, as dust to gas ratio increase, we see that nitrogen, the color, purple color, the nitrogen abundance is decreased, a negative correlation. This is not a surprising case because the nitrogen chemistry in the dust environment is generally in the gas phase. So as it's also attributed to the CNO cycle, not the nitrogen abundance is not generally attributed to dust phase chemistry. That's why we have seen this trend, and also here helium trend is also in negative correlation. My time has finished. So let me. Okay, here is the HR diagram of our sample by using Miller-Bartolini 2016. So most of the objects here you can see they are young. Most of them are younger than 2000. And here are the results which I have already told. This is the summary of the results. And our future work is, yeah, you can. I shouldn't read, no type. Okay, thank you for your attention.
Can we put the conclusion?
Questions? Any questions?
Thank you for your presentation. In your slide 9, I saw that you compute electron density, and you have pretty large values of electron density. Some of them are than 10 to the 5, what diagnostic do you use to compute that densities?
I agree with you. Some of them are extremely large. We shouldn't have expected such quantities. So when I show you our tables, I will even show you the color. Here, not here. Can you, this, effective temperature. We see here very high effective temperatures, but for some of the objects, although they have high effective temperatures, they have low excitation class. This is a bias. This makes the samples outlier. There may be more than one reasons, but what comes to my mind is that their photo ionization simulations, they should be recreated, checked, because we do not expect such low excitation for such high densities, and these kind of objects, there are three in our sample, show high, very high or very low data numbers. So the objects, the outlier ones are here all marked in black circles are outliers. These are the ones that we shouldn't expect high temperatures, and also they show two of the objects show very high gas to gas ratio, although they have very high temperatures. These are outliers.
Yeah, but I meant with what diagnostic do you use to compute such large electron densities? Which lines do you use?
Okay. The highest, we use the photoionization code outputs, and they use sulfur, in some cases, helium.
Okay, any last question? No, let me ask. Do you have any information about the morphology of these sources? Because we will learn from Denise that they affect greatly the line ratios that we see.
Yeah, we chose all the objects from Hash database as they all have angular diameters less than 8. So we assume that they are all compact objects. We assume they are all spherical. So we use the Claudipod, assuming them as spherical. They are.
But did you resolve the objects or?
No, they are so faint. Also for our faint object spectroscopy. Camera, and we don't have material or knowledge to resolve them.
Okay, thank you very much. Next speaker is my very good friend Carmen Sanchez Contreras, who's going to be talking about the forsaken. The forsaken ones. Okay.
Thank you. Hello, everybody. Yes, thank you for being here after the coffee break. I really appreciate it because I'm going to be talking about boring pre-planetary nebulae. I'm sorry. Not because I am a masochist or because I got tired of looking at these messy guys that some of them have been newly classified as whatever objects in this meeting, but because I truly believe that we need to look beyond this kind of nebula, to understand the full diversity in pre-planetary nebulae. So I'm going to be focusing in objects that have no extended nebulosity in HST images. Okay.
So, yeah, well, I think we all know, agree that studying post-AGV objects that are making the transition now between the AGV and the planetary nebula phase are key to understanding planetary nebula shaping, right? But studying these objects, we also know that is not easy because pre-planetary nebulae are short-lived and rare, and only a fraction of those get to be well studied, right? Of course, well studied is a very relative and maybe subjective concept, but what I understand by well studied is at least some multi-wavelength data and also some spatially resolved emission maps of CO, because those guys, most of their mass is molecular. So if we want to understand what the real structures are and the dynamics, we need to have COs. And of course, what are the objects that normally get all the attention? Well, these ones, right? I mean, the objects that have spectacular morphologies and kinematics. But are these representative of the whole class of PPNs, or are just these ones extreme cases? I mean, it is worth studying. We are learning a lot about these objects, and actually they help us to set strong, stringent constraints on the central sources. But I think we cannot overlook anymore PPNs that look boring. So based on these previous studies, mainly on those kind of objects, we reach this conclusion, no? All PPNs show complex non-spherical shapes. If this is true, and if binary is actually the driver of these changes, then this is a little bit problematic, because then what happens with what is the progeny of single to low intermediate mass stars around these PPNs? Where are? Of course, this statement is only true for the PPNs with spatially resolved nebulosities. But the thing is that there are many PPN, bona fide PPN, right, that have no extended nebulosity identified in HST images, okay? But they meet all the criteria together with the other ones to be PPN. We know they have, colors, infrared colors similar. They also have other indications of circumstellar material. So we should not overlook these guys. So this is the goal of this project that I initiated recently, to try and see if there are strong biases or some biases in our previous studies of pre-planetary nebulae and try to mitigate those. How? Well, just trying to characterize in some detail these forsaken PPNs. So the first stage, we just picked a sample of about 30 forsaken PPNs that have HST images but show no hint of nebulosity around it. And then we went for CO line observations to see if we can characterize the circumstellar gas around. We used the iron perimeter antenna first, and then ALMA. So our first most basic goal is just to understand what kind of structure is hosting the circumstellar material that we know it's present there. And this can be done even without angular resolution, can be done just by looking at the profiles of CO, right? At least we can, this can help us distinguish in two broad categories of PPNs, right? The ones that have just massive outflows, right? Which typically show profiles like this with the intense nervo component and some wings. And then the disk prominent objects, the Van objects, that have very spiky narrow CO profiles. So even without angular resolution, you can have a good idea of these two categories. And of course, we want to go beyond that, and of course, to try and derive some of the envelope parameters, no importance, like, for example, to investigate if there are multiple kinematic components to determine the average both velocity, the mass loss rates, etc., as we would do for the flashy PPNs. So the work I'm presenting here, which is in progress, had partially or mainly comes from the excellent master thesis of these two students over here, Paula Lopez and Paula Muñoz. And so they worked with our data. We first started looking at the iron fertility data. We had observed 16 sources, and we found a high detection statistics. This is actually higher because the ones that were not detected in CO with iron have been later detected with ALMA. So that this was actually confirming that there were circumstellar outflows in even if the HSD images didn't show anything at all, any nebulosity. So in many of the cases, we just find what we call shared profile, which is suggests that these objects are dominated by slow AGP-like outflows. In some other cases, we found wings, which is indicating that they are developing fast ejections. Okay. Then, of course, we went to ALMA, and it has much better sensitivity, and it also deals better with ISM contamination of the profile. So we managed to detect all the sources, or many more sources, like these ones, for example. And also we confirmed the presence of wings, broad wings of emission in many. Okay. Of course, the main advantage of ALMA is that it has a spatial angular spatial resolution. And even though this program was not designed to get very high angular resolution, we have been able to resolve the envelope of all these objects, right? So I'll show you. For example, the low velocity component, the core emission, the narrow core, is tracing, normally a slow, roughly round envelope that is consistent with being the remnant of the AGV star. And we find some morphological diversity. We find some of the objects are kind of elliptical, oval geometries, and in a few cases also detached shells. And the expansion velocities are the typical ones for AGV groups. Then the wings. For those that have wing emission, which was about roughly half of the sample, we found that the high velocity emission comes from a much more compact region closer to the center. And even if the emission is compact, in some cases it is, actually in most cases it is partially resolved. And as you can see in this position velocity diagram here, we can even see some velocity gradients, in the jet, which is always consistent with this being post-AGV with bipolar post-AGV. Okay. This is another example of a source with post-AGV bipolar wings. And well, these are the typical kinematical ages we find for this compact component, less than a few hundred years. Okay. And we also have other objects that show distributions more complex that we probably are telling us about more complex structure or kinematics, and we are still trying to figure out what it is. We also, it is interesting, but we also only found one object with this kind of narrow, spiky CO profile that is typical of rotating disks. We can even see probably some gradient here. We have to work on that, but it's most likely a rotating disk. And then there is only one CO non-detection with ALMA, but it doesn't mean there is no circumstellar gas. It means it is ionized because we detect the 830 alpha recombination line. So it is already planetary nebula, maybe. And the profile is very funny. You can see it has these two horns, and it's very similar actually to what we got for the red square nebula, which we studied in more detail. And it ended up being a rotating disk. So maybe this is another candidate for. So we estimated the masses for the objects in a sample, not for all of them. This is still in progress, so we have a subsample of them. And we find masses between 0.1, well, up to 0.1 solar masses and mass loss rates in this range. So if we compare these values with those obtained from previous samples of PPNs, well, it seems that the forsaken PPNs could be maybe less massive, a little bit less massive than the flashy PPNs, and also have probably lower mass loss rates. Okay? We also look at the expansion velocities. Here, the results are not so clear. There is a big difference. Maybe Forsaken has in general a little bit larger expansion velocities for the AGV wave, but we don't know. In general, we don't find super highly extreme velocities for the post-AGV. But this has to be looked at in more detail. So what it seems, in general, I think my feeling is that the Forsaken PPN are younger in general than the most cherished or the flashy ones, right? The configuration where you have a round halo, big round halo, and then the small jets just starting to emerge from the center goes in the direction that this could be NASFEM pre-planetary. So, work in progress, but some preliminary conclusions. Of course, even if the HST images don't show any nebulosities, these guys have circumstellar outflows, long and fast, at least one or two might have rotating disks, and the Forsaken could be less massive and certainly, I think, younger than most well-studied PPNs. Future work, well, there's a lot to do, of course. We need to complete the sample and probably even adding more that are already in the literature, but I think there are more hidden there. And of course, we want to do a more accurate characterization of the properties of the envelope, just looking at all the CO transitions we have, and actually we also have other lines from other molecules. And one important thing is also to study separately the slow and fast component. Important things that we want to look at, for example, if there is an extensive linear momentum in the fast outflows and all the others. Eventually, we want to understand what are these Forsaken PPN, and perhaps, I don't know, maybe find the progeny of single lobe intermediate stars in this sample. But, well, I think in general, even if we don't find these guys in this sample, I think it is, at least I hope this project will help to mitigate the bias in these studies and hopefully will help to get a better understanding of these systems. So stay tuned, this has just begun. We have lots of things to do, not only analyzing the CO data, but of course, trying to gather multi-wavelength data and new data and data to understand well, and put all this information together with what we have from the flashy ones and see if we can improve a little bit our understanding. And yeah, well, thank you very much.
Thank you for thinking, but that's boring.
No.
Questions, David, so run.
Thanks a lot, a really nice talk. Can you go back to the slides about the rotating disc, the red square?
Right.
So can you explain a little bit more how you infer for what the disc is like? Because I understand the two spikes being the disc, but why is it so asymmetric?
Well, this is because the H30 alpha transition is measured. It's been amplified and it's very sensitive to any minor changes in the physical conditions in the disk. So it's not, I cannot tell you the left peak is higher than the other because of that, because at other epochs is the other way around. I mean, it's just very sensitive to any changes in the physical process. And this is kind of, there is mass loss going on, there are fluctuations, so it just changes. But the double horn profile is very characteristic of a rotating disk. And actually it emerges, this kind of profile emerges for this line. But for example, for H39 alpha, it's just a Gaussian or Lorentzian profile. So it's at some point, the line becomes horny, and this is telling you that there is a disk.
Thank you.
Sankwok.
I'm sorry, I missed how many or what percentage of the sources have extended CO wings, like CRL 618.
Roughly half of the sample, so like, well, half, a little bit less than that, maybe 13 or 12 or something. And I think these are a younger version of an object like 618, for example. 618, you can see the halo, the AGB halo, and the cavities, you know, that have been excavated by the lobes, and these are already pretty large. I think in that case, it's like 15 arc seconds or something. In this case, it's just at the beginning of the process. Much more compact.
Typical velocities for the wings.
Well, this is here. They are not super high velocity. There is one object that reaches up to 150 kilometers per second, but actually I think this is the disk object, so it's not sure if this one might have a disk and an outflow. I don't know. But the rest, this is of course our projected velocities, because we haven't figured out yet what is the inclination of the sources. But you see, it's not super high, less like 70, 60. And that the same happens with actually with the rest of the nebula. I mean, the guys that have this super extreme velocity, for example, 618 is probably one of these ones, or each of the one as well, are only a few.
Again, the circumbinary disks are not smooth. They have blobs because the two stars producing torques in the Lagrangian point and so on. So these blobs can be seen in rotation. Probably that's what you are seeing.
Are you talking about the object that has it 830? Yes, I guess so. If I had the spatial angular, high angular.
You told us that sometimes the blue is higher.
Red square nebula, which is different one.
Yeah, varying physical conditions.
Yes. And actually, for this object, we have two epoch observations. We see this change in the profile, and also we see changes in the free continuum flux. We see changes in the mass loss rate. So we have a similar study for 618. Well, it's what Pablo presented the other day. We see changes. I mean, the post-AGB winds are changing on timescales of few years, actually, changing velocity, changing the mass loss rate. They're doing things, yeah.
Joe, last quick question.
Very quick question. I should know the answer because I'm on the team, but what percentage do we see the photospheres? Are there spectral types determined for any of these objects, or are they all too obscured?
No, I mean, these objects are forsaken, so that means there is not much in the literature. So I think maybe for a third or a fourth of them, there are some tentative spectral classification in the literature, and they are F-type, G-types. There are also some objects that are OH-IR stars, classified as OH-IR stars, but no spectral type. And I think out of the whole sample, most of them are like a star dominant. I mean, you can see a bright star. Maybe one or two are very obscure, and it is not clear what the counterpart of the object is in the HST images.
It's interesting. Okay, thanks. Okay. Muchas gracias, Carmen.
De nada.
Our next speaker is Theo Khoury. Oxygen isotopic ratios.
So, hello everyone. Great to see so many people still here. We've almost made it to the end. So it's very good that Carmen's talk was before mine, because it's very nice to see these samples of this post-AGB studied in this spatially resolved molecular line emission growing. And the idea with this project was to add another dimension to that type of study, which is looking at the isotopic ratios, in this specific case, oxygen isotopic ratios, which are linked to how these stars evolve. So there's a lot of people involved in the study, many of which are here. And yeah, Joel's question, the last question in the people's talk, was also very relevant as a segue into what I'm going to talk about. So just to get everyone on the same page, we will be talking about these objects in this phase of the post-HB, where the mass loss rate on the HB has stopped, and they are on their way to becoming a planetary nebula. We'll try to stand on this side. For the objects in this study, I selected fairly obscured stars, and that was following a previous study we did on the water fountains, which are the green squares here. This is just a color diagram with infrared magnitudes. And I'm going to talk about 6 objects and then focus on only 4, which are the red pentagons and the blue pentagons, which are the sea-rich and oxygen-rich. So this is the type of data we got with ALMA. This is the type of data we got with ALMA. We observed, I'll talk only about CO isotopologues, so 13CO, C18O, and C17O. As Carmen said, for a lot of them, we detect these high velocity wings that I'm showing here in the 13CO line. And what I find really cool to see is that when we integrate the emission in these high velocity wings, we get these point symmetric structures, which are in some cases slightly displaced from the center, in other cases occupy a large distances from the star. And yeah, so they have these morphologies, even though we didn't select them for that. Yeah, so then I'll focus on these 4 objects exactly because they have determined spectral types. And I thought that was a very interesting thing that we hadn't thought about before, but I think it adds a lot to the study. And so these 2 are carbon-rich, these 2 are oxygen-rich. They are all very famous. They're not one of these forsaken sources that Carmen was talking about. So first, I'll talk about deriving circumstellar masses and timescales from the observations we have. I'll talk about oxygen isotopic ratios, and then a little bit about evolutionary timescales from theory. So I used the C18O line because it's optically thin, so it's easier to analyze than even 13CO, which can be optically thick. And because we expect the abundance of this isotopologue of CO to be the one that varies less for stars in the mass range that we are looking at. So this integrated emission of C18O that we observed. And the very first thing I did was to calculate timescales of the envelope based on the size and the expansion velocities we see, and derive gas masses, and then use those 2 numbers to estimate average mass loss rates over this post-HB timescale that we derive. And that's what we get. I also put here the spectral types that will come in later. But what you can see is that we find relatively short timescales, up to 1,000 years, maybe a little bit more for some objects, and fairly high gas masses, which imply average mass loss rates, which are quite high. There is one object that Bruce also talked about a few days ago, for which we know the metallicity as well, and this also adds a lot, as you see later. If we didn't know the metallicity for this object, we just assumed solar composition as we do for the other ones, we would derive a much lower circumstellar mass here. Massa also talked yesterday or 2 days ago, I don't know, about M192, and they get higher mass than what I get here, but they did a more detailed study, so you should probably trust that number more. So then now moving on to the oxygen isotopic ratios. These are the values we measure for these objects. And now we can talk about a little bit how we expect these oxygen isotopic ratios to vary. So for most stars, that will happen only in the first dredge-up, when especially the 17 oxygen abundance in the outer layers will be affected by convection. And that will set the value for most sources. But in the case of more massive stars, so above more or less 4 solar masses, during the thermally pulsating HGB phase, you can have hot bottom burning, which should in principle destroy all, or to a large degree, 18 oxygen in the envelope. So then if we see stars that have basically no 18 oxygen, you can be fairly confident that they have gone through hot bottom burning. And then you expect carbon stars to form somewhere here with these two limits still somewhat uncertain, and to have oxygen-rich HGB stars, or oxygen-rich post-HGB stars there. And if we look at the models, for instance, of Caracas and Lugaro, with the Monash code, and we look at different metallices, we can see how these models predict how the 17 to 18 oxygen ratio would vary as a function of initial stellar mass for different metallices. So we have the region where we expect carbon stars, the region where we expect oxygen-rich stars, and the region where we expect bottom burning sources, way out of this scale. And Javier talked about this in the third, I think, talk of the conference. So then we use this type of diagrams to just convert the isotopic ratio we measure to some initial mass. And I know people might think that this is not known well enough for that to be done, but the idea is indeed to get as many constraints as we can to compare to these evolutionary models. And what we find is that our stars are more or less in this range, so between 1 and 2 solar masses. And one of the motivations for doing this type of studies is that a lot of these sources have been suggested to be massive stars, especially for the work I did before on the water fountains. That was the case. So the idea was to see, well, so then we shouldn't see any 18 oxygen, but we do, and we find that they should have relatively low initial masses. And I was thinking about this yesterday a little bit. So I did a back of the envelope calculation and this is a point for discussion that I would like people to maybe react to later, is that we shouldn't see a lot of these stars with more than 4 solar masses. So maybe we should count how many we think we have and see if that makes sense, because they should evolve faster as well. So we shouldn't really be catching a lot of them. Okay, so now I made it to the last point. I seem to have still a lot of time, which is good. So now what I'm going to do is to compare the evolutionary timescales that I have derived, which I take as an upper limit to the phase that they left, or to the time since they left the HGB, to the expected evolutionary times for stars with these initial masses. Yeah, so then I look at the models from Marcelo, who is here, so he can make sure that I don't say anything wrong. And what he does is that he defines the beginning of the post-HGB phase when the mass in the envelope is 1% of the initial stellar mass, which are these red dots there. And then if we look back at the circumstellar gas masses that I'm deriving, that have been spelled in less than this time scale, it means that all these objects would have more than 1% of the initial mass this time ago. So we can be confident that they were way above this line in those that much time ago. And then what I did was to look at his evolutionary tracks, and he predicts both the time since that point to spectral type F0, more or less, and then another time scale from here onwards for different initial stellar masses. And then what I get are these expected evolutionary times here. which when we compare to the timescales, to the kinematic timescales that I'm deriving for this massive molecular envelopes, they are much larger. So I thought that wasn't something that I was planning to look into in the beginning, and that we could only do it because we had these spectral types for this object. So I thought that was very interesting as well. And just to point out that this source, even though I think I'm calling it by a different name than what Bruce did, was also in his presentation and doesn't seem to have a companion at the moment, at least. Okay, I'm going faster than I thought I would be. And then I also saw Semi Phillies. I think I don't know if that's how you pronounce your name, sorry. But I saw his talk in which he was calculating this cooling timescales, was also in one of the first days. And then he was finding that the kinematic ages were, well, he was getting faster timescales than expected from evolutionary models. And then I thought, that's more or less what I'm getting as well. So then I put my points there, very close to zero. As you can see, these very young recent ejections and his objects already in the cooling track. And then being an astronomer, I fit a straight line there. And I get that this is about twice faster than what you'd expect. So that might be something to test more or pay attention to. In other objects as well, maybe with Carmen's objects, you can also put them here and we see if they fit this line or not. Okay, so I made it to the end. I think there's a lot of things that we can learn from looking at this, a lot of different constraints for a larger sample of post-GP stars, and that's what I'm pursuing, to get more of this 17 and 18 O ratio determined for many sources, and also trying to get visible spectra so that we can determine the spectral types and perhaps even the metallicity. I think there's a lot of work to be done theoretically on how this ratio varies actually. And there are some simplifications that are done now, especially regarding the initial value of this ratio that I think can be improved. But I think if we do that, we'll probably learn a lot about these post-HGB objects. As we have talked several times, we think that these objects went through binary interactions. But I think a lot of these results are also very useful to understanding how that happens and what's the fate of these objects. And yeah, this is about the evolutionary timescales that I talked about now. Thank you.
Thank you very much. There are questions? Also.
One is not a binary because it was in Bruce's sample, the other three you don't know?
Yeah, exactly.
You don't know.
I don't know. Maybe Javier knows more about M192.
Okay.
But we suspect that we don't have, we haven't.
Yeah. What we say in the paper is that being as low mass as these objects seem to be, we don't know how they could sustain such high mass loss rates to have created this envelope. So yeah, we suspect they were all binaries at some point.
Marcelo over there. Uh-oh.
Hi, first of all, thank you very much for this talk and also for the work in particular. And also this, I think that this mean mass loss that you are estimating, that this might be very useful for us in particular, because those are the kind of, that regime of mass loss is completely unconstrained. We don't have many things to put into our models. So, but my question, because I think I missed something, is this timescales that you estimate with our models. What is it, from which point to which point is it estimated?
I think that I'm estimating them from this model, from this point to their present spectral type. So some of them are B0 stars. So I'm taking the track or I'm interpolating between the tracks.
And you are starting from this arbitrary definition of 1/100th of the solar mass.
Yeah,
Okay, makes perfect sense that the models are not doing well, I guess, because in fact, what we need to get a very good, not the prediction, but a good time scale is we really need those mass loss that you're estimating. So it would be nice to see what the models give if we add those, because the earlier, let's say, the first part of the evolution. Can you go back to the other diagram? No, the one with that one. The part you see that there is a part which is rather horizontal, that is dropping down. And without let's say there is a part in which you remove the envelope without changing the effective temperature very much. That part of the evolution is really defined by the mass loss rate, and we don't have good mass loss rate for that. So using your mass loss rates for that part would be very interesting, and then estimating the time scales. Thank you very much.
But are you talking now about the post-AGB mass loss rate, or?
Yes, in that particular region of the diagram.
Incoming with.
I think HUV will not call that thing an HUV stuff because it's rather like some.
Hi, thank you very much for the nice talk. It's just a comment. You said that we probably got the mass right. No, I think that, remember you use C18O as a fixed abundance, and from that you derive the mass. We did it taking 12CO as a fixed abundance, and we derived the mass within a factor of 2. And I mean, being two different methods and getting about the same result, I think we cannot be. I mean, it's already too good to.
It's probably somewhere in the
really
middle.
worry about it.
Calvin?
Yeah, I was going to say that we have to be careful interpreting these mass loss rates with the post-AGV mass loss rate, okay? Because this is huge, right? And there is another way of, well, this value is just obtained dividing the mass by the kinematical age of the nebulosity. And this is something we've been doing for many years, right? And we figured out it was too high. And another possibility to explain that is that most of that material was already in the AGV wind. And then what you have is a jet that has a very high momentum that is accelerating that material. But it's not that, it is related, but it's not a direct measurement of the post-AGV mass loss rates. If you want to have a good measurement of the post-AGV mass loss rate at present, then the way I figured out was to observe the emerging H2 regions that are just developing in some of the objects. So you can see really very close to the central post-AGV. And those are still larger than those adopted by the models, but are a little bit lower than these ones. So like, for example, in one of the objects in your sample, HC3 1475, there is a jet that is coming out right now from the central star, and it has a lower mass loss rate. So somehow it's good to look at everything. And I was saying this just in case Marcelo is going to plug this huge mass loss rate in his model, but then it's gonna get so crazy.
Yeah. But the thing is that for these H2 regions, you really need relatively high expected temperature correlation. And the thing is, the region in which I'm interested, because there are not many constraints, is when they are still rather cold. So this is, let's say, this transit, even between the post-AGV and the HGV, there is this region which is still too cold to be maybe a post-AGV, but it's rather hot and already, it's not really the HGV.
Yes, in Theo's sample, actually, he has one of these objects, and one that has the.
I think we need to go.
Yes, can I?
We need to proceed. Hans, hold your question for the selection. I'll be Hans Theo again. Last but not least is the talk by Rudy. Probably one of the most funny titles that we have here in the conference, talking about getting the most from X-ray data. And he is the expert.
Thanks, everybody. Thanks for sticking around that you have. Giving the nice stuff. You notice I snuck in a second talk. I got a first talk in the first poster session. I'm an astrophysicist at the CFA, Center for Astrophysics, Harvard and Smithsonian. I work for the Chandra X-ray Observatory. And my opinion is that Chandra is awesome. I think it's pretty undisputed. I made this out of yarn, not X-rays. Crocheted, and we have a lot of fans online who do really cool things, like make Lego Chandras. Chandra is still operating, it's still functioning. We still have an oversubscription ratio of like a factor of 5. But we are not limited by much except for funding. And that's what we're currently facing right now, uncertainty in that direction. To the point where when I go home October 6th, I may not have a job. Sorry. Such is life. We're gonna take a little deep dive into BD plus 30, 36, 39. Many of you may know this nebula. We're gonna take a deep dive as far as what Chandra saw, starting with the very early observation that was done in the first cycle by Joel and folks here, who you may see some in the room as well. They studied this object and they see this. This is the HST imaging here. And then you see over here the X-ray observation. You'll notice that there's an asymmetry. There's a bright spot in the X-rays there. And this was really interesting to Joel. He can tell you more about it later, but ultimately they fit the X-ray emission, found it was about 2 to 3 megakelvin, and seems to be consistent with the first unambiguous detection of this hot bubble that was long predicted inside of these planetary nebula. Unambiguous because the Chandra X-ray Observatory can actually spatially resolve the bubble and actually determine that it's truly extended. Previous missions had seen X-rays from this object, but there was mostly all within the PSF, so you couldn't really tell the spatial extent very well. Move forward a little bit. A couple of years, this asymmetry led Joel and others to consider if there was a possible explanation for the asymmetry in the X-rays, and they looked at the extinction maps in this object. So this is BD plus 30 again. This is different energy bands. So the cool thing about the Chandra X-ray Observatory and most X-ray observatories is that you detect individual X-ray photons. And so you can actually just interrogate the list to just get the X-rays in a certain energy range. And that's what Joel's done here. This is the full broadband, this is the soft band, medium band, and hard band. These are all relatively determined in terms of energy. Hard means it's the highest energies, soft means it's the lowest energies of the X-ray photons. And then put that onto what the AV extinction map that they derived from other observations looks like, just to try to explain if this could account for the asymmetries that you see here. Go forward a little bit more, we got more observations. Young Sam Yu, who was Joel's student at RIT and my office mate, Chandra also has gratings that can slide into place. Those gratings disperse the spectra spatially, and so you get a very high angular resolution, high spatial resolution, high spectral resolution dispersed image of the object, and then from that you can determine a really great, excellent spectrum. This is what that spectrum looks like. It may not be great to y'all, but it's great to us in the X-ray community. I have a zoom in here just to show you that there is a model line plotted there, along with the X-ray data in black and the model line in gray. Just to show you that, yeah, there is a model that we can fit to this. That model is actually a 2-temperature model. So Young Sam argued in the paper that this requires 2 temperatures. You couldn't get the X-ray fit without doing the 2-temperature models. We can turn this into a flux spectrum now that we have a model for it, and you can see there's a whopping amount of carbon in this hot bubble, which also led to other works later showing that there's this ionized carbon is actually crossing the contact discontinuity and recombining with nebular material. But I don't have that on this. So I have a little interlude now just to tell you about why this title of this talk is called Down to the Last Drop. So this is the observation from 2000, the first observation. It has about 4,000 counts. This is the first cycle of the mission. So sensitivity was really great. Fast forward about 9 years later, same 19 kiloseconds, same exposure time, and you get almost half of the counts. If we go to 2024, this is a simulated observation based on this one, just so randomly drawing the right amount of photons. You get about 15,000 counts in 19 kiloseconds. And then 2019, you get 344 counts. And I didn't even project this later to now because it's just really sad. You can't get the photons anymore. The reason for this is that there's a contaminant that's building on the detector window. There's an optical blocking filter that keeps the optical photons from coming in. It's getting thicker, and it's getting thicker because in the harsh radiation environment of space, the spacecraft is actually probably materials ablating off, and it's going to the coldest spot, which happens to be that optical blocking filter, and it's just adhering to it. We talked about baking out to try to fix that, but it's really risky, so it's not going to happen in the immediate future. So we're losing soft X-ray photons, but we still have all the other bands all the other X-rays that we detect with almost the same efficiency that we have since the beginning of the missions. So this is why we still have a high oversubscription rate. But for X-ray astronomy from planetary nebula, it's pretty much done. It's hard to do. It takes too much time. So that leads me to this work, which was just published in 2024. This is the work looking at the archival observations of this BD plus 30, 36, 39. Again, here's the X-ray observation. You see the asymmetry. Like Joel showed, when you made different energy band images, you're actually taking those photons and then making a curated list. You're losing some information in that. So instead of doing that, I decided just to take each individual pixel, which, for example, that one has over 200 counts in it. And some of these have fewer counts, but they have sufficient amount of counts that you can start doing statistics on them. If you do a statistic called the median value or the median energy value of all the X-ray photons in each pixel, you get something that looks like this. I'm just showing you now where the smooth X-ray contours are on top of that image. And I want to point out that you don't see that asymmetry in this statistical image here. And you see a very different morphology than what you see here. You can look at that in different ways. This is here in X-ray counts. This is in the median energy, and this is the radius from the central star. And you can ask yourself, what's the median energy of one photon? It's nonsense. So you can filter that out, and you can clean up this image quite a bit like this. And this is what I'm going to show you from now on. So this is the median energy image. This is the X-ray image. And then this is the HST H-alpha image. And the contours from this image overlaid onto that median energy image, which has now been smoothed. And the first thing you'll note is that it's very closely aligned with the nebular morphology. You can extract the spectrum from those regions from the X-ray spectrum. You can fit them, and you can find that you end up needing to have a column density that increases from the central region to the outward region by a factor of 3. And here it is again. You can take this a step further. This is the extinction map based on the H-alpha and Paschen alpha. And you can make an extinction map, and you can try to actually correlate these two on this plane. This is the column density here. This is the median energy value. And this is what a different thermal plasma looks like in this plane. And it doesn't look good. This is arguing for a 3 megakelvin plasma for the central region and an even hotter plasma for the outside, which is what you expect because a higher median energy means you have a higher temperature. But it's actually probably not what's happening here. You can also draw, infer a column density if you assume it's 1 temperature plasma, and you can compare that to here, and then you end up with what you need is an excess, and this is the excess column density that you need. I was just playing with these methods just to understand if I could get something better, but ultimately none of these work. They don't work, and it just suggests that it's not wherever the ionized nebular gas is, that's not what's actually contributing to the extinction or to the hardening in this median energy image that we see. Instead, I looked at this observation here, and I compared it to this, and it looks really similar. We have the same ring. I'll even see some structures where You get harder where it's brighter here. And does anyone know what this observation is of? It's an old observation. Thank you. It's of the PAH feature, the 3.3 PAH feature from this paper in 1994. And it's just showing that there's a lot of dust in this nebula as well, just outside the ionized gas. And that's probably where most of the absorption that we're seeing in this median energy image is coming from. So I have a little segue here. Now that I have 4 minutes, I think I saw, and my timer also suggests that. This is a little interlude just to show you what things look like. This is NGC 40 in in 2 mass. And this is the X-ray observation of this object. Right, this is the X-ray observation bend, so you get more signal. Do you see the hot bubble? Still nothing smooth, because sometimes smoothing helps you see things better. No, nothing. But if you look at this region in the space and you make this X-ray spectrum like this, you can see that there's an excess of X-ray photons here. If you limit yourself to those photons, now do you see it? Oh, wow. Yeah, and then you can blur it and it looks really impressive. Am I right? So when you look at this paper from ours in 2005 and you see this beautiful hot bubble, this is where it came from. I just want you to know it's those mattering of photons there that you can only do because Chandra has a really low background, lower than XMM, lower than anything that's going to come on the market in the future. And so it's really powerful for that reason to do this type of techniques. This is a paper object that's also the Chan Planet Survey, which we're wrapping up and doing the hot bubble, all the hot bubble measurements that should be coming out soon. And a student of mine, I have this thing that I overheard Joel say one time, because I was his PhD student at the time.
True, I'm sorry.
And I said to him, he set me up, he said, you're gonna look at this object, we didn't detect anything. Tell me what we didn't detect. So I had to calculate an upper limit, and in that process, I came up with this and I sent it to him and I said, I think I did something wrong. There's a hot bubble there. And he was like, yes, hot bubble there. So I've been working with undergrad students in the summertime because that's about the capacity I have with all of my Chandra duties to do research. And we've been doing looking at different things with the X-ray photon list. We've been applying some machine learning techniques to do some clustering algorithms. This is one in particular that's going to be in the Chan Plan's paper. It's complicated, but essentially we take each photon and we just collect the nearest 8 or 10 photons, and then we calculate some statistics from those, and then we use them and then we plot them as a function of radius, and we use them to better pull out these faint detections of sources. This is what NGC 40 looks like in this plane. You can see that's the hot bubble and that's all background. This is what NGC 7009, that's the hot bubble, that's the central star emission, and that's all background. So we can filter out the background by making cuts in this plane and get really clean images of the X-ray observations. That's NGC 7027, just for comparison. But you can see that this really stands out as clearly that's different, and that's the hot bubble that we see. So we're working on that and should be out soon. Those of you who are on the original Chan Plan's paper should be getting an email from us within a couple of weeks. Thank you.
Thank you, excellent talk. Questions?
Very good, two very good questions. And sorry if you already mentioned it and I missed it. The first is, what are the energy ranges of the bands?
The energy bands that Joel did, so all of the X-ray photons we get from BD plus 30 are from about 0.3 keV to about 1.5 to 2 keV. And so the energy bands he drew for those were probably up to 0.5 and then 0.5 to 0.8 and then 0.9 onwards, because that's where the neon line is.
And what models have you done the spectral?
The model that they're all APEC models, which are optically thin plasma models with different abundances because for BD plus 30 especially, you have to vary the abundances because it does have different abundances than most planetary nebula. It's one of these carbon-rich, hydrogen-poor objects, Wolf-Rayet, like central stars.
Rogelio and then David.
Well, you told that to adjust the plasma model, you needed two temperature component. But that was, well, my guess is that for that, you assume like a collision and ionization equilibrium. But sometimes when you get like these two plasma components, that means that you have maybe collisions or something, and there's a collision of the plasma, and maybe using non-ionization equilibrium could be like perfect. I don't know, did you try in some time try to do that?
For the data that Young-Sam Yu presented of the high resolution X-ray spectrum, I don't think he considered non-ionization equilibrium models. Jesus and I have looked at them to try to figure out if they can make sense. But but so far we don't have enough photons for most of the objects to really decipher between those two cases. If we had more photons, definitely we could probably have some distinguishing characteristics to hopefully roll between those two, but we don't right now. We were hoping to get some with the XRISM satellite, which is a high resolution X-ray spectrometer with Japan and the US. But there's a gate on that detector that stayed closed and they can't get it open. And so we don't get soft X-ray photons from it as a result. And so we can't do the work that we wanted to do with it.
Okay. David?
Thanks. So in your obviously unbiased opinion, you said that Chandra is the best and forever be the best, right? But yesterday we had a really nice talk about eROSITA that fished out a few more X-ray emitters and then mentioned the prospects with Einstein. Can you give an idea of whether we might be able to carry on doing some of this stuff with Einstein's probe?
Yeah, I think one of the reason why it was the best for this kind of studies is because of the high spatial resolution and the low background. There's nothing like that right currently in operations. You don't have the high spatial resolution in eROSITA. eROSITA is great. It's not we're going to reach the depth that it was going to reach, so it's really shallow for our purposes, but you can still find some things there. Einstein probe sounds like it has a really good sensitivity, but the PSF there is I think I saw 11 arc seconds or an arc 24. So we won't resolve a lot of these things, but I will make a plug for the paper Jesus and I did on XMM observations of NGC 5189, this really wild multipolar object. It has a hot bubble and we did not expect to see that hot bubble at all. It's there, it's huge. We could probably do a map with Einstein probe if we were able to propose on that mission.
Yeah, the advantage of eROSITA is that it's mapping the whole sky. The disadvantage is that it stopped mapping the whole sky because Russia is one of the partners. So because the Russia-Ukrainian war, then Germany stopped the collaboration. So they have turned off the satellite for the time being. So it was expected to be providing data releases as they were integrating more and more photons, and so also to provide the two regions of the sky. So at this time, what has been released is the German half of the sky of the first data release. So for the time being, eROSITA is not going to produce more data. Who knows the future? Any more question? Hey, Vincent, please.
Thank you very much. That'd be fascinating. If I'm straying off the subject, I will be corrected by the chairperson. But I'm wondering about X-rays in general, because you focus on hot bubble, you have very, very interesting history. But with some of the hydrodynamic models, we do expect soft X-rays along the jet symmetry axis, in particular, if you have the formation of cross shocks, X shocks, like you have in jet exhaust. Would it be a subject for discussion to ask if there are any other soft X-ray observations that are relevant?
Yeah, Raghvendra has looked at post, or is it, what do we call that object? It was one of,
At 1475.
is it proto?
Survey of feedback and just exactly for the reason that you're saying. So we did a little survey of pre-planetary array, looking for X-ray emission. Because of course, these have these high velocity outflows, so you expect shocks. The only object that we detected was HE 3-1475. In hindsight, that is not surprising because that is the one which has the highest velocity outflows that we see, about 1,000 to 1,000 drop per second. And for CRS 618, we did a paper in which we estimated what we would have expected based on our hydro models of the outflows that we see there. And unfortunately, in the observation that we had for 618, the sensitivity was not enough to detect.
Mendel 3 is also, Mendel 3 is probably symbiotic, but symbiotics, you show the soft X-ray emission a lot.
But you got emission at the center star.
Yeah, and also emission at the center. I failed to point out, but I don't see, is Stavros here? No. Oh, are you the one that was arguing that the BD plus 30 is bipolar based on?
Bipolar, no, elongated.
Elongated. Yeah.
For this reason, you see slightly the X-ray also.
Yeah.
It's
asymmetry.
Yeah, it's asymmetry, and I think if I remember correctly, because the work 10 years ago, there is the optical. So the model shows that there is a offset of the axis, and probably it's a high velocity gas.
Yeah, CO.
Sorry?
CO outflows. Yeah, no, it's that.
And the optical, I think if I remember correctly.
It's got two CO
Balls
coming
sides.
but they're on they're
Yeah.
this way.
So in the paper, we also argue that to get this kind of hardening on the edges, you need a lot more material than if it was a nice elliptical nebula. And so it probably has to be elongated.
I have been checking that.
Yeah.
Yeah, it's true. And I had no idea about the old data with the pHs because this probably it's a good idea.
Yes.
There is a disk or something there.
Yeah.
Because you need high density, which I haven't implemented in my code.
Yeah, and the map that you get from the optical emission is not necessarily going to pick that up because that may be closer to the central region and the nebular emission may be further out. And that's why you don't see it. I think you don't see it in the extinction map.
And I don't remember, there was another work after mine using, trying to model. I don't remember if their model, it was more, they had implemented a disk or something like that, a torus or something. I don't remember, I have to say. But yeah, it's.
Thanks.
Okay, so thanks again, Rudy. And now we can start the discussion. So if you allow Joel and I to lead this, so we can take maybe 20 minutes for discussion, and we have the lunch at 1:15. And then before having lunch, I'll provide you a short summary. I hope it's going to be more funny than scientific. So we may start with Hans' last question.
Okay. It was a question to Theo, because one of the objects is anti-process enriched, and it is quite low in mass. So does that also constrain the initial mass?
So you talk about HD 187885, right? Yeah, so that's the object that we had, the metallicity, and the S-passage enrichment from your spectra and study, and it's also carbon rich. So, and we find a very low mass for a carbon rich star, but the metallicity is also low, and low metallicity is easier to form carbon stars. So that can be an indication that the lower mass limit for forming carbon stars is actually lower. I remember there was a paper by, I think, Albert recently, in which he pointed out a similar thing for another object now. So I think it might just be that the third dry job can happen efficiently or even low mass.
So on the way down here, are your mass, your inferred initial masses consistent with the luminosities of these objects? So they're slightly lower luminosity?
So a lot of these objects don't have very well constrained distances, so people just place them where they would like based on how luminous they want them to be. But we found that the luminosity that we would infer from the mass are about inconsistent with distances that people have been using, with the exception of N3 1475, which several people have put at 8 kiloparsecs, but that's way too far for what we.
Yeah, no Gaia data for those. Was it Sun or Javier? Javier and Sun.
Yeah, just a remark on my fellow comments on mass loss at the beginning of the OCGB. The APM1, I was presenting M192. Of course, it was 12CO, 120. Now we are working with 17O and etc. But you know, this 1200 years dynamical time and one solar mass was already present 30 years ago. And since that, we know those numbers for at least, I would say, 40 objects, and there will be more objects coming. So it's just a matter of, you know, putting all these numbers into the codes and see what happens. And then after this phase, you have the radio recombination lines that's tougher, but you can also put those numbers when the central star becomes a bit hotter. So the numbers are there. Probably the most critical point here is that we see these dynamical times, but we don't know whether if all this mass has been released in a single event or what. And remember that we also have Van-Winkels objects. Those are also OCGBs. The typical masses are 100 times less, but we don't find all the mass that the OCGB has lost to become OCGB, which is the problem. But those numbers are already there.
I'll run back here now.
I also had something that I wanted to add to this mass loss rate discussion. So indeed, as Javier just said, we don't know if this was a one-off event with an extremely high mass loss rate or if it's a continuous process. And I think we have enough data to start answering that question. For instance, if we look for correlations between kinematic ages and circumstellar masses, those should look very different for a one-off event and for a more continuous process. So maybe that's a question that Carmen can already find in the data for all the sources that she has. I think it would be very interesting to start answering that.
Hello, this is also a question to Theo. One of your objects, HD18 or whatever, which I remember to be IRIS 19500, is one of the very few objects which we have found to show the 21 micron unidentified infrared emission feature. Now, this feature is extremely strong, and after 30 years, still have not been identified what the carrier is. Do you have any thoughts about this?
That's for Theo.
That's easy for me.
I have a very short answer, which is no. But I'll give a slightly longer one. And I think it's related to what Hans just said before, that it is a peculiar object in the sense that it has a low metallicity and is also a carbon star. So maybe those things play a role, could be some clues to what you look for.
Typically carbon.
I want to say that it might be due to the
Highly ionized, yes, because I just said theoretically, the highly ionized cation of the fullerene have a great contribution on the 21 micron. at least at the theory, but I don't know what will happen over there. PAH, hardly, even in experiment or even the theoretical work that we had done with Professor Paul Hadley. Mostly there might be the mounds which are more flexible aliphatic aromatic, yes. So there are the spectrum of that, but again, if in that object there is no CH stretching or no CH bonds and it is only related to carbon, then for now, based on my understanding, I can say that might be due to these catalysts.
More on that topic.
Yeah, I got a question for Sylvia. Yeah, so for a long time it has been the understanding that bipolar planetary nebulae descend from non-massive progenitors, and there is evidence because we see those closer to the galactic plane, so they have a lower scale height. You are saying that more dustier AGB stars, they are also descending from more massive progenitor. Do you see or has been investigated the scale height of those dustier AGB or post-AGB stars?
So in general, we have that, yes, the amount of dust that we observe, especially during the HB phase, increase with the mass. But this is something especially true for the carbon-rich star. So this is true for that. Then, so we have this increasing trend with the mass for the carbon, so until 3.5 solar mass, more or less. But then, for the masses that have initial that start to have the hot bottom burning, the amount of dust that is formed is less respected to the carbon because it changed everything, changed the mass loss, it changed also in general the amount of dust that we are able to do. So yes, we expected to form more dust. So in principle, I would agree with that. But with the ones that are very massive, such as the oxygen-rich ones, produce less dust in the end. There are also less abundant, so the contribution that they do is less prominent with respect to the carbon-rich sources. So it depends. But the sample that I studied of the planetary nebula was only with the round and elliptical sources. So I do not study also the polar shape. Something else.
Oh.
Also, I have a question for you, Steven, because when you presented your graph that it has the initial mass during the AGB phase that you pointed that it is in the initial mass or in this phase. So does it mean that do we have to take into account now how much mass has been lost during the red giant branch? Because then it will define how much mass is when it starts the AGB phase, right?
Yes, so this is one of the other uncertainty that we have about the low and intermediate mass revolution. So yes, it is necessary to take into account also the mass that is lost during the RGB phase. There are some new studies that I really suggest you to have a look, which are from Tailo and Milone 2025 that study the mass loss for the RGB sources. And they claim that the amount of dust, the mass loss, the amount of mass that is lost during this phase is something around 0.2, 0.3 at maximum mass loss, solar mass. So you have to add to my number, this is 0.2.
I'll call on myself. And just to come back to a couple of things that were raised in the first few talks today. I know everyone's tired and it's, so I'm looking at the faces, can't we get to lunch? and go home, which I think is reasonable, reasonable thing to think, but, there were several talks that were talking about jets, and of course, Noam started the meeting out talking about jets and jets. Bruce Ballack has often said, but by the way, we all miss Bruce, I know he wished he could have made the trip, to be here, but, you know, Bruce Ballack has said over and over again, there are these unseen jets. Vincent mentioned, gee, can we detect these jets in X-rays? And I think the general consensus, those among us who were observing in X-rays with Chandra at the beginning was, oh, we thought jets would be easier to detect. The young stellar object community thought jets would be easier to detect in X-rays. And it's surprising, actually, that, you know, maybe it's consistent with the models, the sort of low X-ray luminosities that are seen even in jets at, you know, 300 kilometers per second, where you'd expect self-shocking and so on. Very few were cleanly detected with Chandra even. So where are the jets is my question. And several people in the you know, Mohammed, Mohammed had very strong theoretical arguments for the presence of an 800 kilometer per second jet. We would love to have seen that in X-rays in that object. I don't know if we ever looked at it or not. But you know, they don't seem to show up. Menzel 3, maybe NGC 7027 show X-ray jets. So
How about M192 that has these two blobs, and if they're actual shocks?
I think Raghavendra, one of us tried for M192 with Chandra at some point. I don't remember.
I think it's got a serendipitous observation, but it's not.
You need very high velocity shocks.
No,
for this
the
X-ray.
velocity at the node is around, the projected is around 70 kilometers per second.
No, but if, for instance, in M192, these two blobs, during this conference, they were introduced as spheres, right? Well, if they're actually X shocks across the axis, the shocks could be dynamically stationary.
Yeah.
And the flow through them would have a shock jump that would possibly be visible in soft X-rays.
We need to spend another few $1 billion on a sub-arc second resolution X-ray imaging.
So connected to that, one of these objects that I showed, M3 1475, has these beautiful jets of ionized gas that go up to 1,000 kilometers per second, I think. And we see the molecular CO that goes up to a few hundred kilometers per second, like interweaved with the ionized emission. And those are thought to be like stationary shocks, like Vincent just said. But I had also a question for us. In your model for the jets, there was a empty region in the middle. Is there supposed to be a jet core there that is kind of entraining things, or?
So the MHD models do not predict mass in the axis. It's really the disk wind effect. But the data shows that we need some mass there as well, but not a lot. Because so if you just use the MHD model, then you will see a hole into the absorption component, and we don't see it. So there must be some gas in the axis itself as well.
And I should mention, I guess, that, you know, these young stellar objects obviously show jets in optical emission lines, so the jets are there. It's just that we don't detect them in X-rays very much.
Yeah, I think jets are there, and they are very difficult to see, but like for example, Hans is seeing jets in, you know, at least in those kind of objects. The problem, I think, is they are too cold, because in pre-planetary nebulae, the outflow dominant, let's say, of classical pre-planetary nebulae, I think the only jet that has been directly detected and spatially resolved is also seen in absorption against the background emission of the source, which is HG3 1475. So there we see a jet is collimated because there are long slit observations, you know, across the source, and you only see that absorption in the central one. So it is collimated, but it's cold. Okay, you only see it in absorption. It's actually the blue part of the BCE profile, and relatively cold, and it's relatively tenuous, but it's fast. And that's but actually, if you do the numbers with that jet, that is the one that has been ejected most recently, you don't get the high linear momentum extent. I mean, it doesn't seem that jet is the one that produced the rest of the thing. So it seems that the jets also vary. They do whatever they do, and then they just relax and hide. So make things very complicated for us.
We talked about the S's and we talked about the fact that they're not all the same. So there's jets and jets and jets, and there's things that are not really jets, but they look a little bit like jets. So Hans's jets they're just cold outflows from a situation that makes it, but they're not the same things that we're looking at, like Marco's jets, as in, fast outflows in a conical shape, are different once again. One point I wanted to make about those jets, the ones that he's seeing, but they're not, I don't know if to call them jets, but they are collimated outflows in common envelope simulations. There were some simulations that he showed when we looked at the grid that don't show them at all, right? So there's quite a lot of variability. In one case where we know the common envelope has got quite a nice geometry, we understand reasonably well, at least from the kinematic point of view, but they don't always show those nice conical things. So there's a lot of diversity in the common envelope itself. And in that case, it would form quite a variety of outflow shapes when we get to the PN phase.
Yeah, I mean, I was saying this before, and the community has to be careful, but it's called jet and what is not jet. There's a very strong definition of it, as I was saying, highly relativistic, strongly common developers. I mean, you don't do yourself a favor if you call everything jet.
Yeah. In some of the common envelope simulation you showed with the grid, I think they were not yours, they were
Yes,
the other
I
students.
mean, there was students, but
There's a
so the
variety.
ones which didn't show jets, jets.
Yeah.
Yeah, the culminated outflows are not that far evolved. That's also one thing which is so we cannot tell by now, but probably there was involved. Actually, the dynamics are similar. We don't expect to do them more.
Maybe just one final point on this on the common envelope jets, not jets. The common envelope PN, which have been looked at extensively, have a variety of morphologies. They're not all jetty or a collimated or bipolar. They have all kinds of bizarre things. And of course, there's projection, orientation, and age of the nebula that plays a role as well. But there's definitely a variability.
So what's the minimum velocity for a jet? 100 kilometers per second, 200.
Sound speed, how's that?
The sound speed of
About the sound.
but of that's too low.
Supersonic.
When there's discussion with the observers and the theorists, the people mostly talk about velocities, and I understand that because that's readily observable if you do well. However, from the point of view of comparing with theoretical models, the Mach number, as I think I mentioned before, is much more relevant. So all of you who not only observe velocities but also observe temperatures, so that you can actually make plots and maps of the Mach number, please do us a favor. Okay.
We wish we had all the information, but sometimes we don't.
That's right, yeah, I know it's hard.
So now we're kind of getting to the end. I'm going to take the risk of derailing the discussion completely.
That's fine.
So also I said at the start of the week that we don't need any more data, we just need to know how to treat the data better. But then I see talks like Hans' talk, which is just an abundance of data, which demonstrates the amazing stuff you can do when you have your own telescope. Yeah. And it spills out into all the other talks. I just tried to go through the program of the talks about binaries, and I think only one talk on binaries dared to show a radial velocity curve that wasn't from the Mercator. But the Mercator is great, but it's modest, right? And comparison is the thief of joy, but I compare our community to the exoplanet people who manage to make the equivalent of the Mercator and steal 3 telescopes, Northern Hemisphere, Southern Hemisphere, dominate all of the time. And so my question is, what can we do as a community to go in that direction to make sure we get more time to have an 8-meter Mercator in both hemispheres?
See, a real conversation with Daddy.
Guerrilla tactics.
Talking about solar plant where it's combined with this.
Yeah, we need to find exoplanets around binary stars.
Yeah,
You know the people.
Don't fight the enemy, join me. Okay. Any more fields for discussion? Yeah, okay, so I see that people is kind of waiting for lunch. Okay, so if so, let me then provide a summary of this meeting. Of course, this is going to be incomplete and biased view of the meeting. It's going to be complete because I'm trying to catch up all the time with the meeting. There were so many interesting talks and scientific discussion that I was a bit busy, so it's been impossible for me to get there. Bias, of course, because there are different scientific interests. But this is just as many of our papers, so we are used to it. So we have 87 attendants to this meeting, more than 20 countries, and more than 60 oral contributions and 30 posters. So from the scientific point of view, there were enough contributions to the meeting. I'm really very pleased to see that observations are still surprising us. So we are finding a lot of new things which are challenging the theory, are challenging our understanding. So we are finding those niggly around eclipsing binaries in the LMC. Yoga doesn't know what they are. So if she doesn't know, who else is going to know? Nodes, hydrogen 2 nodes everywhere, sometimes with high velocities, and in this tiny planetary nuclei that Harriet was showing. And then we are discovering coronal lines in planetary nuclei. And this is thanks to the use of integral field spectroscopic observations, which are really very useful. And Jorge is also finding this kind of emission, like iron 5 and 6 emission in the very well-known ring nebula. So it's really amazing that such objects so famous that they are still surprising us. Then nickel and iron clamps. What the heck is this? It's so amazing. When I saw the title of this talk, I said, "Oh wow, this is something completely new." And then we should try to stop Albert to find more stars, because it's been for 2 to 3 to 4. So next time he's going to say he has discovered a cluster of stars inside the And then there were a lot of observations, very interesting, but if I tell you, I have to kill you. So very sensible material there. A full range on TC1, those are really amazing results showing us that there is a complete physics about these molecules that we don't still understand. Those nebulae around possibly star that was presenting Arturo, or the common envelope phase, the simulations and the result presented by Jason. So these were really amazing, but I'm sorry, I cannot tell you anything more. Then the monsters, you observe, you get surprised, and sometimes you see those kind of monsters in space, and it's really very amazing. So I wonder whether these are really planetary nebulae or something else, because all these morphologies of these shapes, the extremely high expansion velocities with all these things that we see there, they are quite unique. I remember Noah's words that don't say planetary nebulae are unique, because all of them are unique. So you don't need to say that any longer, but still I think so. Elvira and Steven on the portrait were presenting those kind of monsters as well, that we don't really understand why we see those bizarre ejecta in these sources. And then there are simply objects that they don't behave properly. So you have this oxygen isotopic ratio versus CO, and they don't follow the expectation. And well, maybe don't following the expectation. They are telling us that the policy really us who are not understanding what's going on there or the binaries. So Bruce has been looking for binaries for years, decades, and where we expect to find them, they are not there. So he was showing that we need to make a very careful sample selection to be able to find those. Then is everything in the right place? Jaroslav, Thomas were showing us that maybe some of those PN, they are not PN, they are symbiotics, or maybe they are in long-read nova. So fortunately, Quentin and Joa, they keep discovering new planetary nebulae, so we are increasing the number in spite that there are bad people stealing them from us. And then, well, we were wrong before, and then there are people that are telling us that we were wrong and they are correcting us. Santander Garcia was finally showing the model for the Ring Nebula. I don't know how long this is going to last because this model has been changing over time. Raul was showing us that the tides are very important in the system, and so maybe we're going to be safe from the tide. The correction factors, they care about the morphology, and this is something that we have not done before, so we need to take care about this. And also, Palmira was showing us that when we are computing the dust mass and temperature, we really need to be very careful in the selection of the dust grains geometry that we are using, because our estimates may be full by what we see there. But what do you do when everything goes wrong? You add the cosine of this. And this is going to solve all your problems. But remember, very, very important thing, don't put the important information at the bottom left corner of your slide, or no one is going to see that. Okay, so finally, that was a session I love very much with this PT 1159. I've already sent a SAR born again, so I will finally get into some agreements. So there were properties were matching as for the chemical abundances of the central stars and the nebulae, but I know that he doesn't care about morphology, but we have to care, and Paulina was showing us that we really need to care about the morphologies of the nebulae around those sources. We also see that PG 1159 they have less mass and they are cooler, less dust mass. Sorry, that were very well connected results. So those planetary nebulae hydrogen portion that they have greater turbulence, and then Janis was showing his model that this is because the mixing of the material after born again ejecta. Still, the details need to be fixed. We don't understand this the differentiation, the different this sample there, and we need to know why is this dichotomy. And there are new X-ray detections in planetary nuclear for stars. They are bright, but maybe not that bright as Rogelio was suggesting. Noam. Yeah, this is a real jet in a binary system. And so we see the jet at different scales. Here we have seen just a new ejecta of material coming there. And this is because we are being held because we know the accurate orbit of this system. So this is the kind of case study sources that we need to translate what we see in other systems. By the way, I'm not really adding anything of this today sessions. We all have this very fresh in our mind, but actually Hans is doing an excellent work on discovering these binary systems. and I really enjoyed most of the talks that we have today. I was not in the first session here, but I was in my office finishing this slide, still with the YouTube and listening to the talk. So, Lohan, I saw your talk. Okay, so we are young then, we are still, well, maybe not the five from the HIFA meeting in 1994 that we are still here, but actually I'm very, very glad that I see so many young people in this meeting, students, very young postdocs. So I'm really feeling that the community of planetary is rejuvenating. Maybe not in the US, Joy, but everywhere else. And then I have a message very important for you. See, I put on the right corner, not the left one. So have our postdocs hired. So if we care for our people, then we'll make it stronger our community. There is one word in Spanish that I like very much is ojalá. It comes from the Arab wa sha Allah. So God wish, God might, so that something is going to happen. And what we expect is that APM X is going to happen. X is for unknown. And so the stock hasn't been able to find still the place. So there are different places, maybe Greece, maybe Brazil, Israel, or Mexico. So we are still talking to the different options. Maybe in the near future or mid future, we'll let you know. I wish, ojalá, that we met there in a few years. In my opinion, which is my humble opinion, this meeting has been a big success. And I don't know whether it was because of the conference banquet, the place, the beauty of Granada, the culture that we have here, or just because we spent time with friends and we were talking all the time about science and about ourselves. So I think that it was really a great success. And so people were all the time attending the conferences. So the attendance has been very high during all these 5 days. So people keep their eyes open, listening to the talks. But most of them. But another factor that makes this meeting a big success, in my opinion, has been the log members. Janice was taking care of the computer of the time. She fixed everything. You tried to broke everything. There was one person, one of you, I'm not going to say the name, uploaded the talk 13 times. 13, 1, 3. Oh, it was you. It was Theo. So I'd like you to give a big clap for Janice. And she did even when it was her birthday. This May. Another person I like to appreciate very much was Faisal. She's got the most unpleasant task to keep the time. She's the timekeeper, and you can see the faces of people when she was showing the 4-minute earlier. They saw the devil, but I mean the time was very, very compressed. Thanks to our friend Non Sober, who wanted to have as many talks as possible and discussion time and time for lunch. Oh, that's not needed. And so she made this meeting happen to be on time all the time. So another big part. So there were also some people in the law, Edgar Ivan Santa Maria, who made he made this law for the meeting, and he made the poster, and he's been helping on all this technical stuff. And finally, Rogelio, on the very first day here, I said, could you help with the meeting? I said, oh yeah. He didn't know he had to run all the time around with the microphone. So please, another big clap. I really appreciate the SOC. They were able to build this fantastic scientific program we have in this meeting. So the program to me was stunning and very well designed, and there were some of the sessions are just like magically put together so that every thought was like talking to the other. So I also want you to provide a clap to our SOC members. Yeah, so we are talking, we are starting work on the next meeting, and we are also considering new additions to the SOC. So just try to reduce the average age of the SOC. I also appreciate the help by the IAA. They provided us with this conference room and with a lot of services here, like the opportunity to have the picnic out there. And finally, also Fernando and the Laura company, the events who were able to run this very properly. But to me, what they didn't make this meeting happen and be a success was you. Thank you.